In this video, we are going to talk about antiderivatives. For the past couple of weeks, we have been looking at taking derivatives um, for a number of different functions, and then also focused on some of the applications. And here we're going to be going in the opposite direction, determining what a function was if we were given the derivative of it. We're starting here with a definition of what an antiderivative is. We're taking two functions to have the same letter, capital F being maybe what we started with, and then when we take its derivative, we end up with this lowercase f. So if we were to go in the reverse order, saying I have something here, it's a derivative. What was the original function that I started with? So that's what we mean by an antiderivatives. We had an example in class last week where we were taking functions and sort of trying to guess what the original function was if we were given the derivative. So looking at this picture over here on the right, we said, well, if I had something that the derivative was, say, 3x squared, we sort of guessed that the original function was x cubed, because we said, well, if we were to take the derivative here, we bring the 3 down in front, drop the power down by 1. But we could have had, say, plus 1, plus 2, plus 3, plus 4, plus some number here. And still, when we take the derivative, we still would have gotten that same answer, because when we take the derivative of that constant, it just goes away. And so you can see in this picture here, this is what we're showing, is that all of these functions with different values of c added onto the end would have the same derivative, in this case, this. So in the example, what we're trying to do is find the specific one that meets the criteria that we're given, that there's a particular point, 1, -1, on the original function. So the way that we would solve this is we're saying, okay, I have some function, it's a derivative, and its antiderivative, let's say f, capital F of x, is going to be x cubed plus c, some constant. I'll take the initial conditions that are given, knowing that f of 1, plugging 1 into the function, is going to give me the output of -1. And so solving this equation, I would get that c is equal to -2. So for this particular example, and we can see that in the picture, the function in question that we would be wanting to consider is x cubed minus 2. This function has the derivative of 3x squared, and it also meets the criteria of passing through that point 1, -1. This slide gives some of the general formulas that we use for antiderivatives. And again, this is thinking about what we know about derivatives going in the reverse order. The most common rule that we've used is the power rule. And so if I started with a particular function and I wanted to go in reverse, rather than dropping the power down by 1, I'm increasing the power by 1. And rather than multiplying by that exponent in front, I'm dividing by that new exponent. So it's kind of the power rule in reverse. All of these ideas that we see down here with trig involve the chain rule. In this case, I have some number k that's being multiplied by x. And so thinking about this as a function that I take its derivative, the derivative of cosine is going to be negative sine, so I've got that negative out in front. And then I would multiply by the derivative of the argument here. So I would multiply by k. So when I multiply by k here, it's going to cancel with this k that's in the denominator. So again, these are just formulas that are kind of going in the reverse of what we have, what we've been doing with taking derivatives. I'm going to go through a couple of examples. And then just a couple important ideas down here below, that if I have a constant k that's multiplied by a function that's kind of just along for the ride, we just kind of keep it there, same as we've been doing with derivatives. And then if I have two functions that are added or subtracted, when I take the antiderivative, I can take those separately as separate components. All right, let's do some examples. So, in this particular first example, we are given the derivative, and we're going to try to go backwards to find what the original function was. So again, when we take the derivative of a power, we bring the number down in front and drop the power down. So in the opposite direction, we're going to add 1 to the exponent. And then rather than multiplying by the exponent, we're going to divide by the exponent. And we always tack on this plus c because there could be some constant for whom the derivative was 0. Let's just think about if I were to take the derivative of this. Let's see. The 6 would come down into the front. I would drop the power down by 1. The 6 that's down in the denominator would cancel, and yeah, I would be left with x to the 5th. And the plus c, if we took the derivative there, we would just have 0. All right, let's look at letter B. I'll rewrite this as x to the negative 1/2 power. I can follow the same idea that I just did in letter A. I'm going to raise the power up by 1, so that'll be x to the 1/2. I'm taking negative 1/2 and adding 1 to it, and then divide by the new power 1/2. So this is 2 times the square root of x, and then we've got to put that plus c onto the end. Looking at letter C, I know that the function cosine has negative sign as its derivative. So if I change this to be negative cosine, then when I take the derivative, those negative signs will cancel out. And the chain rule says that I need to multiply by that 2 on the inside, so I'll put a 2 in the denominator to balance out the taking of the derivative. So again, if I were to take the derivative here of this capital H of x, I would have a negative sign of 2x. And then I would multiply the whole thing by 2 because of the chain rule. Those 2's are going to cancel, and the 2 negative signs are going to cancel, and I get back this function that I have here. Looking at letter I, same idea. I know that the function, if I started with sine and took its derivative, I would have gotten cosine. So I think that this is going to be a sine function. And rather than multiply by the derivative of the inside, I'm going to divide by the derivative of the inside. So I think that my original function would have been 2 times the sine of x over 2 plus c. Looking at letter I, or sorry, J, we know that the derivative of e to the x is just e to the x. So I anticipate that I would have just e to the negative 3x. But because I know that I have to multiply by the derivative of that exponent, I'll counterbalance that with a negative 3 down here. Again, if I were to take the derivative of this, I would have e to the negative 3x. And then we multiply by the negative 3. The derivative of c is just 0. So I end up with this value back. Letter F. There's a formula for taking the antiderivative of an exponential function like this. So I'm going to write that here. If the function is a to the k times x, this is on the slide before, the antiderivative is 1 over k times the natural log of a times a to the kx plus c. In our example, let me make a little line here. In our example, a is equal to 2, that's the base. K is equal to 1. There's no number being multiplied in front of the exponent there. So plugging that into this here, I'll have that the antiderivative is 1 over, there's just going to be 1 here, natural log of 2, and then we'll multiply by 2 to the 1 times x plus c. Simplifying that, we have 2 to the x over natural log of 2 plus c. I know that many of you had some version of calculus in the past in high school, and so you're probably familiar with this symbol, which is the integral sign. And this is the symbol that we use to mean find the antiderivative of the function that's in question. In this case, it's called the indefinite integral because we don't have any bounds on it. An example would be find the integral of x squared, and this differential dx means with respect to x, with respect to the variable x. We saw when we were looking at differentials earlier in the semester that we can take derivatives with respect to a different variable, and so we can also do that with the integrals. Talk about that later. But this would mean find the antiderivative of the function x squared. So we would raise the power up by 1, divide by the new power, and add a 3 on. And so this would be the integral of x squared. Later, after the next exam, we will be looking at applications for the integral that have bounds on them. Maybe we're going between the values of, say, x equals 1 and x equals 3, and determining something about the graph within a particular interval. All right, thanks for watching, and we will do more examples in class.